at that time, here's a little bit of a closer story close to us, is that my lab and my students were thinking, the real world is not about 20 objects. The real world is a little more than 20 objects. So following the work of Pascal Visual Object Recognition Challenge, we put together this massive project called ImageNet. Some of you might have heard of ImageNet. In this class, you will be using a tiny portion of ImageNet in some of your assignments. That ImageNet is a data set of 50 million images, all cleaned by hand and annotated over 20,000 object classes. Don't worry, it's not a graduate student who cleaned it. It's that would be very scary. It's Amazon Mechanical Turk platform, the crowdsourcing platform. And having said that, graduate student also suffered from putting together this this platform. But it's a very exciting data set, and we started to put together competitions annually called ImageNet competition for object recognition. And for example, a standard competition of image classification by ImageNet is 1,000 object classes over almost 1.5 million images, and the algorithms compete on the performance. So actually, I just heard somebody was on the social media was referring ImageNet challenge as the Olympics of computer vision. That was very flattering. But here is something that bringing us close to the history making of deep learning. So the ImageNet challenge started in 2010. That's actually around the time Pascal, were colleagues. They told us they're going to start to phase out their challenge of 20 objects. So we phased in the 1,000 object ImageNet challenge. And y-axis is error rate. And we started with fairly significant error. And of course, every year the error decreased. But there's a particular year the error really decreased. It was cut in half, or almost, is 2012. 2012 is the year that the winning architecture of ImageNet challenge was a convolutional neural network model. And we'll talk about it. Convolutional neural network was not invented in 2012. Despite how all the news make it sound like it's the newest thing around the block. It's not. It was invented back in the 70s and 80s. But having a convergence of things we'll talk about, the convolutional neural network showed its massive power as a high-capacity end-to-end training architecture and won the ImageNet challenge by a huge margin. And that was, quite a historical moment. From a mathematical point of view, it wasn't that new, but from an engineering and solving real-world point of view, this was a historical moment. That piece of work was covered by, New York Times and all this. This is the onset. This is the beginning of the deep learning revolution, if you call it. And this is the premise of this class. So at this point, I'm going to switch. So we went through a brief history of computer vision for 540 million years. And now I'm going to switch to the overview of this class. Is there any other questions? Okay. All right. So we've talked about, even though it was kind of overwhelming, we talked a lot about many different tasks in computer vision. CS231N is going to focus on the visual recognition problem. Also, by and large, especially through most of the foundation lecture, we're going to talk about the image classification problem. But now everything we talk about is going to be based on that ImageNet classification setup. We will get into other visual recognition scenarios, but the image classification problem is the main problem we will focus on in this class, which means please keep in mind visual recognition is not just image classification, right? There was 3D modeling, there was perception grouping and segmentation and all this. But that's what we'll focus on. And I don't need to convince you that just even application-wise, image classification is an extremely useful problem. From big commercial internet companies' app point of view to startup ideas. You want to recognize objects, you want to recognize food, you want to do online mobile shopping, you want to sort your albums. So image classification can be a bread and butter task for many important problems. There is a lot of problem that's related to image classification, and today I don't expect you to understand the differences, but I want you to hear that throughout this class, we'll make sure you learn to understand the nuance and the details of different flavors of visual recognition. What is image classification? What's object detection? What's image captioning? And these have different flavors. For example, while image classification might focus on a whole big image, object detection might tell you where things exactly are, like where the car is, the pedestrian, or the hammer, and where the relationship between objects, and so on. So there are nuances and details that you will be learning about in this class. And I already said CNN, or convolutional neural network, is one type of deep learning architecture, but it's the overwhelmingly successful deep learning architecture, and this is the architecture we will be focusing on. And to just go back to the ImageNet challenge, so I said the historical year is 2012. This is the year that Alex Kruszewski and his advisor Jeff Hinton proposed this convolutional neural network. I think it's a 7-layer convolutional neural network to win the ImageNet challenge model. Before this year, it was a SIFT feature plus support vector machine architecture. It's still hierarchical, but it doesn't have that flavor of end-to-end learning. And fast forward to 2015, the winning architecture is still a convolutional neural network. It's 151 layers by Microsoft Asia researchers, and it's called the residual net, right? Is that called the residual net? So I'm not so sure if we're going to cover that. Definitely don't expect to know every single layer, what they do. Actually, they repeat, so it's not that hard. But every year since 2012, the winning architecture of ImageNet Challenge is a deep learning-based architecture. So, like I said, I also want you to respect history. CNN is not invented overnight. There is a lot of influential players today, but there are a lot of people who build the foundation. I don't have the slides. One important name to remember is Kunihiko Fukushima. Kunihiko Fukushima was a Japanese computer scientist who built a model called neocognitron, and that was the beginning of the neural network architecture. And Yang LeCun is also a very influential person, and the groundbreaking work, in my opinion, of Yang LeCun was published in the 1990s. So that's when mathematicians, and which Jeff Hinton, Yang LeCun's PhD advisor, was involved, worked out the backpropagation learning strategy, which, if this word didn't mean anything, Andre will tell you in a couple of weeks. So, but the mathematical model was worked out in the 80s and the 90s, and this was Yang LeCun was working for Bell Labs at AT&T, which is an amazing place at that time. there's no Bell Labs today anymore, that they were working on really ambitious projects. And he needed to recognize digits because eventually that product was shipped to banks and the US post office to recognize zip codes and checks. And he constructed this convolutional neural network. And this is where he's inspired by Hubel and Wiesel. He starts by looking at simple edge-like structures of an image. It's not like the whole letter A. It's really these just edges. And then layer by layer, he filters these edges, pull them together, filters, pull, and then they build this architecture. 2012, when Alex Kruszewski and Jeff Hinton used almost exactly the same architecture to participate in a ImageNet challenge, almost there's very few changes, but that become the winning architecture of this. So Andre will tell you more about the detailed changes. The capacity, the model did grow a little bit because Moore's law helped us. There's also a very detailed function that changed a little bit of a shape from a sigmoid to a more rectified linear shape. But whatever, there's a couple of small changes. But really, by and large, nothing had changed mathematically. But two important things did change, and that drove the deep learning architecture back into its renaissance. One is, like I said, Moore's law. And hardware made a huge difference because these are extremely high capacity models. When Yannick was doing this, it's just painfully slow. Because of the bottleneck of computation, he couldn't build this model too big. And once you cannot build it too big, it cannot fully realize its potential. From machine learning standpoint, there's overfitting and all these problems you cannot solve. But now we have a much faster and bigger bigger capacity microchips and GPUs from NVIDIA. NVIDIA made a huge difference in deep learning history. That we can now train these models in a reasonable amount of time, even if they're huge. Another thing I think we do need to take credit for is data, the availability of data. That was the big data. Data itself is just, it doesn't mean anything if you don't know how to use it. But in this deep learning architecture, data become the driving force for a high capacity model to enable the end-to-end training to help avoid overfitting when you have enough data. So, if you look at the number of pixels that machine learning people had in 2012 versus Yannick had in 1998, it's a huge difference, orders of magnitude. So that was So this is the focus of 231N. But we'll also go, it's also important, one last time I'm going to drill in this idea that visual intelligence does go beyond object recognition. I don't want any of you coming out of this course thinking we've done everything, we've solved vision and ImageNet challenge defined the entire space of visual recognition. It's not true. There are still a lot of cool problems to solve. For example, dense labeling of an entire scene with perceptual grouping. So I know where every single pixel belongs to. That's still an ongoing problem. Combining recognition with 3D is a really, there's a lot of excitement happening at the intersection of vision and robotics. And this is definitely one area of that. And then anything to do with motion, affordance, and this is another big open area of research. There is I put this here because Justin is heavily involved in this work. Beyond just putting labels on a scene, you actually want to deeply understand a picture. what people are doing, what are the relationship between objects, and then we start getting into the relation between objects. And this is an ongoing project called Visual Genome in my lab that Justin and a number of my students are involved. And this goes far beyond image classification we talked about. And what is one of our holy grails? Well, one of the holy grails of computer vision is to be able to tell a story of a scene, right? So think about you as a human. You open your eye. The moment you open your eye, you're able to describe what you see. And in fact, in psychology experiments, we find that even if you show people this picture for only 500 milliseconds, that's literally half of a second. People can write essays about it. We pay them $10 an hour, so they didn't. It wasn't that long, but I figure if we pay them longer, more money, they probably can write longer essays. But the point is that our visual system is extremely powerful. We can tell stories. And I would dream, and this is my challenge to Andre's dissertation, that can we give a computer one picture and out comes a description like this, and we're getting there. You'll see work that you give the computer one picture, it gives you one sentence. Or you give the computer one picture, it gives you a bunch of short sentences. But we're not here yet, but that's one of the holy grail. And another holy grail is continuing on this, I think is summarized really well by Andre's blog, is, take a picture like this, right? The stories are so refined. There's so much nuance in this picture that you get to enjoy. Not only you recognize the global scene, it would be very boring if all computer can tell you is man, room, room, scale, mirror, whatever, cabinet, locker, that's it. Here you recognize who they are, you recognize the trick Obama is doing, you recognize the kind of interaction, you recognize the humor, you recognize there's just so much nuance that this is what visual world is about. We use our ability of visual understanding to not only survive, navigate, manipulate, but we use it to socialize, to entertain, to understand, to learn the world. And this is where vision, the grand goals of vision is. So, and I don't need to convince you that computer vision technology will make our world a better place, despite some scary talks out there. Even going on today in the industry as well as research world, we're using computer vision to build better robots, to save lives, to go deep exploring and all this. Now, okay, so I have 2 minutes, 3 minutes, 5 minutes left. Great time. Let me introduce the team. And Andre and Justin are the co-instructors with me. TAs, please stand up and just say hi to everybody. Can you just say your name quickly and your what year, and just don't give a speech, but yeah, start with you. Your name?
I'm Suvasis. I'm a fifth year.
Fifth year what?
PhD student.
Okay.
I'm a fourth year PhD student in Dali. I'm Bart. I'm a fourth year PhD student in computer science.
I'm Albert. I'm a second year master's student in computer science.
I'm Serena. I'm in the third year of my PhD with Big.
And I'm Hugh. I'm a co-author.
Cool. So these are the heroes behind the scene, and so please stay in touch with us. There are two really the best way, and I almost wanted to say the only way, and I'll tell you what's the exception, is stay in touch through Piazza as well as the staff mailing list. Anything course related, please do not send any of us personal email, because I'm just going to say this. If you don't hear replies or your issue is not taken care of because you send a personal email, I'm really sorry, because this is a 300 plus people class. this mailing list actually tags our email and help us to process. The only time I respect you to send a personal email, mostly to me and Andre and Justin, is confidential personal issues. You know, and I understand if you don't want that to be broadcasted to a team of 10 TAs, that's okay. But that should be really, really minimal. The only time that you send us an email. And also, you know, just again, I'm going on maternity leave for a few weeks starting the end of January. So please, if you decide you just want to send an email to me and it's my due day for a baby, I'm unlikely going to reply you promptly. Sorry about that. Priorities. so a couple of words about our philosophy. We're not going to get into the details. We really want this to be a very hands-on project. And this is really, I give a lot of credit to Justin and Andre. They are extremely good at walking through these hands-on details with you, so that when you come out of this class, you not only have a high-level understanding, but you have a really good ability to build your own deep learning code. We want you to be exposed to state-of-the-art material. You're going to be learning things really that's as fresh as 2015. And it'll be fun. You'll get to do things like this. Not all the time, but, you know, like turn a picture into Van Gogh or this weird-looking thing. So it'll be a fun class in addition to all the important tasks you learn. We do have grading policies. These are all on our website. I'm not going to iterate this. Again, one thing I want to be very clear. Actually, two things. One is late policy. You are grown-ups. We treat you like grown-ups. We do not take anything at the end of the course and say, oh, my professors want me to go to this conference and I have to have 3 more late days. No. You are responsible for using your total late days. You have 7 late days. You can use them in whatever way you want with 0 penalty. Beyond those, you have to take a penalty. Again, if there's really, really exceptional medical family emergency, talk to us on an individual basis. But anything else, conference, deadline, other final exams, you know, like missing cat or whatever, is we budgeted that into the 7 days. Another thing is honor code. This is one thing I have to say with a really straight face. You are in such a privileged institution. You are grown-ups. I want you to be responsible for honor code. Every single Stanford student taking this class should know the honor code. If you don't, there's no excuse. You should go back. We take collaboration extremely seriously. I almost hate to say that statistically, given a class this big, we're going to have a few cases. But I also want you to be an exceptional class. Even with a size this big, we do not want to see anything that infringes on academic honor code. So read the collaboration policies and respect that. This is really respecting yourself. I think I'm done with, these prereq, you can read it. I'm done with anything I want to say. Is there any burning questions that you feel is worth asking? Yes?
What does the midterm exam look like? What's going to be more mathematical, more coding, more concept?
Good question. Andre, do you have midterm?
A bit of everything.
A bit of everything, which means they haven't figured it out. Yeah, we will give you sample midterms. Okay? All right. Thank you. Welcome to the class.